This is lecture 28, and what we're going to be talking about is something that is popularly called u-substitution. It's really a change of variables. The idea is very important in mathematics, and it comes up a lot in very many different disguises. But the idea is that we change from the variable or the reference system that we're in into a new reference system. The letter U is sort of traditional. We start normally with X and Y as the dependent variable, and then we translate from that coordinate system into another coordinate system based on a new independent variable, which is U. So the reason that we do it is we try to simplify the problem, or to turn it into a different problem that we might be able to solve. So the problems that we're working on are antiderivative problems. So here is a typical antiderivative problem. We want to find the antiderivative of x cubed times the cosine of x to the fourth plus 2. And remember that the dx goes here, even though we don't seem to have much real need for it. But as you'll see now, it comes to play a very important part. Anyway, many people can look at this thing and instantly tell that you can do this problem, that you can find an antiderivative of it. If you're very, very good with the chain rule and you understand everything that's been going on, then you would just write the answer down, because it's really that simple. But many people cannot do that, and you need kind of a little step stool to help you out. So what you do is you make a change in variables. You define some new variable called u to help you out in this problem, and you say let u equal. And what you choose for u is a function that is in the problem somewhere that you could reduce down to just u, and it would simplify things. But you also have to have one other constraint in mind, and that is that the derivative of this function u, whatever that might be, is basically hanging around. And the reason that this is all going to work is that, in fact, if you let u equal this complicated mess inside the cosine, this x to the fourth plus 2, then if you remember differentials, du can be calculated, and it's 4x cubed dx. If you just think about moving that dx over to the other side, du dx is 4x cubed, and that's exactly what you've got. But look here, there's an x cubed. Now, there's a 4x cubed here for du, but I've said many, many times that constants can be fudged, and so in fact, what you can do now is translate this whole integral into an equivalent one. If I don't want that 4, I can multiply both sides by 1/4 of this last equation and get 1/4 du is just x cubed dx. Now look, here's dx, and here's x cubed, and here's x to the fourth plus 4, which we said was u. And so this whole integral, this whole thing, can be replaced by the integral of cosine u. See how x to the fourth plus 2 turns into u, and then the x cubed dx turns into 1/4 du. And this whole integral is now seen as being the same as this. But this one, of course, is far easier to do. You can just find the antiderivative of the cosine, which is just the sine. And what about that 1/4? Well, it's just a multiplier. It just sits there. So it's the sine of u. Now, we're finding antiderivatives, and I will go ahead and go along with the custom of when you find an antiderivative, this is where you add in the plus c, because any constant added on to this is going to work. Check the derivative of this. The derivative with respect to u, because this is what the independent variable is at the moment, would be 1/4 cosine of u. And that's what you've got right here. So this is the antiderivative, except now that the original problem was stated in terms of x, we do one more thing, and that is we substitute out the u what it's really equal to in terms of x. So we write our final answer as 1/4 sine of x to the 4th plus 2 plus a constant. And that's our final answer. Now you can check this answer easily by taking the derivative of this thing. 1/4 sits there. Derivative of sine is cosine, that's this guy, of whatever's there, x to the 4th plus 2, times the derivative of what's inside, which gives you 4x cubed. The 1/4 will cancel the 4, and you're just going to be left with x cubed. So that is the right answer. All right. Notice a couple of things, well, at least one thing right now. When I traded out this whole integral, I ended up with an integral that is entirely in terms of the new variable u. So there's u here, and there are no x's. If you find that you've translated from the original problem into an integral that has x's and u's mixed up, then you've messed up. You're kind of like, you've used the transporter beam in Star Trek, and half of you is on the ship and half of you is still on land. That's no good. So you want to make sure that you make the transition from the original x universe into the u universe, and you're not straddling the two. So it is a change in variables, and it gets you into a new universe where you might be able to solve the problem. This is just the beginning. You're going to see in Calc 2 that this idea is exploited a lot, and in much more complicated ways than this. All right, let's try a simpler example. So this time we'll do the antiderivative of e to the 5x. Now this is so simple that I can tell you what the answer is right away without a u substitution. It's e to the 5x, almost, because the derivative of e to the 5x is e to the 5x, except for a factor of 5 that comes popping out. There's no 5 here, so fine. We fudge it by putting a 1/5 plus c, and I'm done. And this is about the way I do most of these problems. I don't really use u substitution, but it is important to know how to do this. So let's go ahead and see how we do this with u substitution. In this case, we would say let u equal 5x. Then du is the next thing that you do. Calculate du, always. As soon as you define u, calculate du. And du in this case is just going to be 5 times dx. Check the answer. Du dx is 5. Yes, when u is 5x, du dx, the derivative of u with respect to x is just 5. So the integral of e to the 5x dx, the antiderivative that is, can be replaced by e to the u. Then if we have du, that's going to give us this 5. So once again, I need to fudge out the 5. So 1/5 du equals dx. So I replace the dx by 1/5 du, and now I'm finding this antiderivative. But that's easy, because the antiderivative of e to the u is e to the u, and that 1/5 multiplier just sits there. And then I get my arbitrary constant, and then we're ready to substitute back in what u was equal to as 5x. So we get 1/5 e to the 5x plus c, which is what I knew already. So like I said, this was an easy problem, but we can see how to do it with u substitution just for practice. All right, let's move on to one that is really important, an example. It's just like an arithmetic problem, but it comes up a lot and in many disguises. What's the antiderivative of the log of x divided by x? Now the trick here is to figure out what to make u. And here's the secret. I'll even write it in a box as soon as I write all the words out. The trick to picking u is to pick for u something whose derivative is, I say, in a colloquial expression, hanging around, just there. Look at the first problem for a minute, the first example. This in the box first. Look at the first example that I had. Oops, way up here. With this horrible looking thing, I chose for u this quantity. And the derivative of it is basically hanging around, just waiting to be scooped up. The derivative of x to the fourth plus 2 is basically x cubed. Yeah, I know it's 4x cubed, but I don't care about the stupid constants. The important thing is the variable. I cannot fudge variables. I can fudge out the constant multipliers with no trouble at all. So you've got to get the basic answer right. So pick for u something whose derivative is hanging around. We're going to exercise this in class a lot. But for now, look for something here whose derivative is hanging around. Well, there's not a whole lot to pick, so it doesn't take you long to say, well, what if I let u equal log of x? Because then du would be 1 over x dx. So this problem just turns into, there's my u right here for the log of x. And the rest of the stuff, 1 over x dx, you see it? 1 over x dx, that's all the rest of the stuff. That's what du is. So what we're doing is substitution. That's why this is called u-substitution. We start with u as something whose derivative is hanging around, and it is, and then we substitute it out, and everything else in this example is completely eaten up by du. So this is about as good as you can get in terms of substituting out something horrible, and it gets translated into something easy. Notice I'm now completely in the u universe. There's no x's left. So this is a simple antiderivative problem where u is considered the independent variable, and the antiderivative of u, of course, would be 1/2 u squared plus a constant. And then final answer, substitute in what u is equal to, 1/2 log of x quantity squared plus c. You can check this answer again by taking the derivative, and you'll find that you get exactly log of x over x. Okay, let's look at one that looks horrible, but sometimes the worse they look, the easier they are. So this is one of the exercises in the book. It's, I don't remember which one, but it's a plus b times x squared divided by the square root of 3ax plus bx cubed. Alright, so this looks absolutely horrible, but the problem is rigged so that it's going to work out nicely if you just choose u to be something whose derivative is hanging around. Now, look at that stuff under the radical. That's the first thing I'd look at. The derivative of that would be 3a plus 3bx squared. By the way, a and b, got to believe that those are constants. There's nothing else that they can be that makes any sense in this problem. Relative to x, they're constants. So the derivative here is going to be 3a plus 3bx squared. Well, that just happens to be 3 times the numerator. So, in other words, the derivative of what's inside here is hanging around, waiting to be scooped up as du. So if I let u equal that stuff under the radical, 3ax plus bx cubed, then calculate du, which is what you always do as soon as you write down u, then you're going to get 3a plus 3bx squared, which just happens to be 3 times that. Oops, sorry, not quite. Made a big mistake. I left out the dx. Alright, so if you want to translate out that integral, you're going to have this stuff under the radical as just u. And then notice that the rest of that stuff, a plus bx squared dx, is, well, what is it? It's 1/3 of du, isn't it? Multiply both sides by 1/3, and you're just going to have a plus bx x squared dx. That's exactly what the rest of that stuff is. So all you're going to do is put 1/3 here times du. 1/3 du gives you exactly the numerator that you want. So this is much, much nicer to deal with than that, because of course we can rewrite this as 1/3 times u to the minus 1/2 du, which means what's the antiderivative of u to the minus 1/2? Well, that's not too hard. The 1/3 is a constant. It's going to sit there. I need an antiderivative, so I jack up the exponent to 1/2. Then I need to cancel that out, so I need to multiply by 2. So this is going to be my antiderivative. Let's just check that because I did a lot of calculations. The derivative of this is 1/2 times 2 will cancel, times u to the minus 1/2, and the 1/3 is along for the ride. So that's it. So consolidating these numbers and substituting back in what u was, we end up with 2/3 of u to the 1/2. So that means just the square root of 3ax plus bx cubed plus c. Right? And that's that. Alright, let's try another problem. This one's fairly simple, extremely simple in fact, if you look at it right. The antiderivative of the sinh squared of x times the cosh of x. Alright, well, you got to remember what the derivatives are of sinh and cosh, but those are easy. They are cosh and sinh respectively. And what do you suppose you should let u equal in this problem to simplify this horrible looking mess? It seems to me like if I let u equal sinh of x, then du is exactly all of that. So du is cosh x dx. And so this integral, this whole big ugly thing, turns into the antiderivative of sinh squared. Well, that's just u squared. And the rest of it is exactly du, which isn't too bad. This is just going to be a simple antiderivative. Antiderivative of u squared is 1/3 u cubed plus a constant. And then you finally just substitute back in what u was. U was sinh of x. So this is sinh x cubed. So I can go there with the cube plus a constant. And that's it. Okay. Now, good time to take a break because we do have one more big thing to talk about. So let's just watch a little program video. No sound this time. So these are little Alice programs written in the Alice programming language. You can go to alice.org and download the whole programming language. And it's actually quite nice, quite simple, very, very, very easy to program. All right, back to work. So let's talk about one last thing with this change of variables business. And that is what happens when you've got a definite integral. What happens when you've got an integral from a to b of some function of x? And you need to find an antiderivative, so you make some sort of u-substitution, right? Well, when you do that, you're going to get some other expression with du, but you see the problem is that this integral, this definite integral, is relative to the variable x, and these numbers a and b, if you remember, those were endpoints of the domain of this function relative to this problem. So they are points where x goes from and to. X goes from a to b. You remember the definition of the integral was you chop up the interval into pieces and you calculate the sum of products and then take that to the limit as n goes to infinity. Well, the point is that a and b and delta x are all relative to x. They're all relative to measuring things in this x universe. When you make a change in variables, u is not the same as x. So a delta x, or a dx, which is what delta x turns into, delta x is not at all the same as delta u. So what I'm going to teach you to do is called a change in variables, where you change the limits of integration as well. Now this is not absolutely essential for most problems, but you need to learn how to do this, especially because it will be specifically requested on the test. I'll talk about the other way to do it, which many of you will already know and have already figured out. But let's do it by example. Well, first, before I give the example, let's say what you have to do. All you have to do is write the following: as x goes from, write all these words, as x goes from whatever to whatever, well, in this case a to b, u goes from, and now you have to figure out what to put in the box here and what to put in the box here. And that will depend on how you set up u in the first place. Okay, and really it's very easy to figure that out. So let's do an example. In fact, we'll do an example that we've already partially done, but without the limits of integration. Suppose we want the integral from 1 to e of log x over x. I love this example. Okay, we already saw that we can do this problem, or at least the antiderivative problem, by making a u substitution. Let u equal log of x. And then du is 1 over x dx. So the problem of finding an antiderivative we did already, and this problem becomes u du, and you just find the antiderivative of that. However, when you've got limits of integration involved, x is running from 1 to e. U is not going from 1 to e. So what you have to do in this problem, before you can change this problem into an equivalent integral, definite integral, you have to determine what the new limits of integration are. So you write as x goes from what to what? You just read that off the integral. From 1 to e, 1 to e, u goes from what to what? Well, because u equals log of x, you just say u is going to go from the log of whatever I put here, the log of 1, to the log of e. Alright? So that means that these numbers become, log of 1 is 0, and log of e is 1. So this integral right here translates into the integral from 0 to 1 of u, that's log of x, and then the rest of it, du, is exactly du. U du. So we can find the antiderivative of that, that's 1/2 u squared, and we evaluate that between u equals 0 and u equals 1. You can see where this would have been fatal if you'd put in the x limits of integration, because u does not go from 1 to e. U actually goes from 0 to 1, while x goes from 1 to e. So you've got to use the u limits of integration, which you determine by writing this sentence. As x goes from the lower limit to the upper limit, u goes from whatever it goes to whatever it goes to. And you can always determine that from that equation where you defined what u is. Okay, so you plug in those limits of integration, you get 1/2 times 1 squared minus 1/2 times 0 squared, 0 squared, and that's of course 1/2. And that's the answer. Now there is another way to do this, I mentioned it, and that is to take your antiderivative as an antiderivative problem. In other words, to change from this log x over x dx as an antiderivative problem to the antiderivative of u du. Okay, find the answer to this, which is easy. That's 1/2 u squared plus a constant, right? But I don't really care about that, because now what I'm going to do is go back to the x universe, 1/2 log of x squared, because that's what u was, plus a constant, and that's going to be my antiderivative, which I then have transported back into the x universe, and now I can take that antiderivative and say this integral, if I don't want to do it by substitution, I can go and write the integral, the antiderivative 1/2 log of x squared evaluated between 1 and e. And when the dust clears, you will see that you get log of e squared minus 1/2 log of 1 squared, which of course log of 1 is 0, so that goes away. Log of e is 1, so you end up with 1/2, which is exactly the same as what you had before. Okay, so here's what I'm trying to tell you. You need to learn to do this, to change the original problem into a new problem, a new definite integral with new limits of integration based upon u. And you can do that very easily. You find your antiderivative, but rely on this equation where u is equal to whatever. Then you write this sentence as x goes from lower limit to upper limit, u goes from, and then you have to figure out what to put in these boxes. And you figure that out by looking at this equation. And you ask yourself, as x goes from what to what happens to u? And it doesn't matter what you wrote. We can answer that question. Just think about this. X goes from 1 to e. Let's answer it with another example up here. As if u is equal to this, as x goes from 1 to e, u would go from 3a plus b to 3ae plus be cubed. Ugly, but easy enough to do. I mean, all you're doing is substituting the low value for u, which was 1, the high value for u, which was e, and then figuring that out. Now, of course, this wasn't a definite integral and didn't have 1 and e, but whatever they are, you substitute them in for x, and you get the low value for u, and then substitute the upper one, and you get the upper value, and you got it. You can trade the integral for a new integral with new limits of integration. Okay, and that is it for this lecture in under 30 minutes. Okay.